Okay, so we're recording now. I do have a question for you all. This is a vote. Even though it's a dictatorship, I'm going to let you vote. How many of you would rather do a statistical project rather than a test?
Yeah. In groups?
Kind of thought in groups. I kind of thought you would say that. I'm thinking we might do that.
Yeah.
Okay? Maybe for the test 4. Okay. Sure. Once we've learned all our statistics, we'll tie it all together. Sure. So I'm kind of glad you said that because I think they're actually kind of fun. And then I will find out if you really did learn anything, and you can apply it to real data in which you collect and you don't know the answer.
Is test 4 the final?
No, it'll be before the final. Yeah, they make me give you a final. So, but anyway, so okay, that was good to know. So we're skipping all the way to chapter 12 today. Thank you for finding the room. I'm sorry it was so goofy, but they told me wrong. So I'm also using this other camera. I hope the sound is good. I don't know, but hopefully it's okay. My camera's not working there, so. All right, we're going to talk about chapter 12, which is probability rules. Okay? All right, so we're going to talk about probability. Okay? And we use it to try to predict an outcome. Okay? Blaise Pascal was one of the first mathematicians to study probability. Now, you may wonder why that is, because the problem is, just like today, he had a bunch of gamblers and they were losing their money, and he said, why are we losing our money? Are we doing something wrong? And he was like, yes, you are. Okay? So, so the idea, probability, I can't spell, probability, is a number between 0 and 1 to describe how often something happens. Okay? And there are 3 types. Okay? All right. The 3 types are, number 1, I'm trying to use, well, I don't like the way they do it, but we'll all tie it all together. Theoretical, sometimes called classical. Number 2, empirical. And number 3, personal. Now the funny thing is they say personal for section 8, the last section, but that's the one I want to talk about first. Okay? So, Keaton, I'm going to pick on you because I know you like fantasy football. Who's your favorite team when you're not thinking about fantasy football?
Like football?
Yeah.
The Patriots.
The Patriots?
Are you serious?
Oh, nice. I'm a Patriots fan.
Everything Boston. Red Sox, Patriots, Celtics.
Yeah, I like you. Okay?
Just give me names.
All right, so after the last 2 weeks of debacle for the Patriots, okay, what's the probability that they're going to win the Super Bowl this year?
100%.
100%? Wow.
They were 2-2 when they won the Super Bowl last. So, I'm the first 4 games.
Okay.
They're 1-2 right now.
I hope you're right, but 100% seems a little high to me.
They're tied for second in the division.
You're a homer, aren't you?
A what?
A homer?
What does that mean?
You like the home team, homer?
Oh,
yeah. Okay. Who else has a favorite team? Jordan does.
I do.
Who's your favorite team?
The Bills.
Well, the Bills, they're rivals.
Not much of a rivalry.
Hasn't been for about 20 years since Tom Brady's been around. But back in the Jim Kelly days, it was pretty good. Huh?
Yeah, they're weak.
Okay, so what's the probability the Bills win the Super Bowl?
101%.
101. Okay, he just broke one of the rules.
Just kidding. Like 30%.
30%. Okay. Well, one more. Who has another favorite team? What's that?
The Saints.
The Saints. They won the Super Bowl a few years ago. Well, there was a guy, and he said if the Red Sox, the Cubs, and the Saints win, that he would get married to the woman, and so then he had to because the Saints won.
Well, the
It
Cubs
was
won
the
after
Cubs.
the
The Cubs,
Saints.
yeah, maybe it wasn't the Cubs, but anyway, the Saints, the Red Sox were in there. I don't remember who the third team was, but anyway, probability the Saints win the Super Bowl.
Oh, I don't know.
We're 2-1 right now.
Something between 0 and 1.
50%.
50%. Okay. How did you come up with that number?
They're two.
You just made this up, huh?
Yeah.
Jordan, how did you come up with 30%?
I was inspired.
You were inspired? Wow, I don't want to get religious on you.
Right?
How about you, Keaton? 100%, how'd you come up with that number?
I was just messing.
You made it up, right? That's what personal probabilities are. You made it up, okay?
Just guessing.
All right, that's what personal probabilities are. We aren't going to spend a lot of time, but they are fun because you can, prove me wrong, okay? So they don't have to be, so the idea is don't have to be based on rules, okay? All right. Oh, we're at the bottom of the board already. Okay. Let's turn this a little bit, okay? I can go down a little bit. All right. So let's also, actually, I want to stay here. I changed my mind. So let's talk a little bit about theoretical classical. They are based on rules. Okay. So let's say, I'll try to pick a nice easy one here. Brock, if I were to flip a coin, what's the probability it would come up heads? 50%. How did you come up with that? Two sides? And one of them's heads, right? So you did that based on rules. Let's do this one that's slightly harder. Eddie, do you play cards?
Of course.
Of course. What's the probability that I pull a king out of a deck of cards?
1 out of 52. 4 out of 52.
Well, you're at 5.
Oh, you're a bad card player, man.
I'm sorry.
Okay, so because there's 4 kings in the deck, right? And there's 52 cards, and so you did that once again based on rules, okay? But we'll talk a little bit more about that. Now, empirical. Let's talk a little bit about that for a minute. Okay, I'm going to ask a horrible question. I'm going to ask the women first, okay? And then I'll ask the men a horrible question, okay? Women, what's the probability that you get breast cancer? Men, before you answer, what's the probability that you get prostate cancer? Those are horrible questions, aren't they? Okay? So we'll ask the women first since I asked the women. What's the probability you get breast cancer? Is it like a deck of cards where you just pull out a breast cancer card?
Genetics.
How do they figure that out?
They're looking at your past.
They look into your past, but I mean, how would you figure that out? Or men, here, I actually know the answer to this question. What's the probability, men, that you're going to get prostate cancer? Do you know?
4.
I think it's higher than that.
It's higher than that.
Don't all men like eventually get prostate?
100%. If something else does not kill you first, you will get prostate cancer. See what you have to look forward to. Okay, the women have it better.
Isn't it like 8 out of 10? I know it's pretty.
No, it's like 100% for men.
No,
It's
for
close to
women,
100%. For women, no, it's not 80%.
Isn't it
But my
like
question is, whatever the number is, let's say it's 30%. I think that's actually pretty close. How would you figure out how to calculate that number? How would you figure that out?
I'm gonna say I'm
What'd you say?
Statistics.
A study.
You do a study, you would do a study, and what would you do in your study?
Pick a number of women and see how many.
Would you do a personal probability and just make it up?
No.
Okay, how do they figure it out? Because insurance companies have to know, right? How do they figure that out?
Yes.
They ask.
Hey.
Okay, kind of.
Oh.
Okay. They measure how often something happens. Okay. If you've got 100 women and 30 of them get breast cancer, your probability is about 30%, right? It's as simple as that. Okay. You can't base it on any rules. I mean, you can try to base it on rules or like genetics, maybe, but you're really going to base that just by measuring it, measuring how often something happens. Catherine.
So like with something like that like runs pretty like deep in like genes and like ancestry or like crap like that, would that technically be more like empirical, even though like it does kind of go off, not necessarily rules, but like it does have more than just like, do you have it or do you not, you know what I mean? Does that make sense?
Yeah, that would be, yeah, more empirical.
Okay.
So the easiest way, because not everybody's going to get a genetics test and find out if they have the breast cancer gene. So, but yeah, more often you're going to just measure how often something happens. And then you might try to find the source. Maybe it's gene-based, maybe it's because you smoked, maybe it's because of you worked at the nuclear power plant, something like that. Okay? All right. So let's talk a little bit about the probability rules, the rules here. And make sure you guys can see there that this gets on the video. Okay? The rule, I already mentioned one of them that Jordan broke. Any probability is between what two numbers? 0 and 1. I always like to joke. Do we have any Cleveland Brown fans in here? Last year, I like to joke that, you know, the probability of them winning the Super Bowl, you might be tempted to say it's negative, but it's always above 0.
We got their first one?
They did, didn't they? Who did beat? The Jets, wasn't it the Jets?
Jets.
It was the Jets. I think it was the Jets.
No, I just made that up because the Dolphins aren't.
All right. The second rule is the sum of all probabilities equals 1, but I'm going to put a rule in here that they don't talk about, if independent. Okay? And I will give you an example of actually a true case example that I worked on. On my master's degree, I worked with a fertility doctor, and we wanted to find the probability that a couple became pregnant. Okay? Because, you know, it involves the man too, right? Okay, so let me ask you a question. If a man and a woman had sex every day for 30 days, would they be guaranteed to get pregnant? Okay? So in that case, the sum of all probabilities would not be 1. They're not independent. Okay? What would it be dependent on? What would be some reasons why a woman might not get pregnant? Does she ovulate? Hopefully within 30 days she's ovulated, but yeah, there could be some irregularities there, right?
Medical issues.
Medical issues? Age?
Wait, are we just talking about the one?
Well, let's talk about the man too.
Oh, well, the dude could have issues.
The dude could have issues. Okay? Okay? It's low sperm count. Okay? Something's wrong in the plumbing, right? Okay? Either the man or the woman. Okay? So, yes, the book doesn't make that thing, but if they're independent, they should all add up to 1. And I will say that if they are independent, they're easier to do, and so we're going to concentrate more on those. The probability an event does not occur equals 1 minus the probability of the event. This is known as the complement rule with an E. We are not complimenting you to complement.
Doesn't equal what? Does that say?
The probability the event does not occur equals 1 minus the probability of the event. Sometimes it's written as this way. Probability of E complement equals 1 minus the probability of event E. Is that better? Okay. And finally, if two events have no outcomes in common, meaning mutually exclusive, you can add the probabilities. Okay, we'll talk a little bit more about that in a minute. Okay? All right, so I'm going to try to bring this over here and hopefully, sorry for those of you watching at home, I know it looks crazy, but I think that's going to be better. By the way, I should ask this question. How many of you watch my videos? Oh, more than I thought. Okay? All right.
I think it only shows the views if we watch it from like the start to the complete finish.
No,
No?
if you click on it for 1 second, it'll show it as a view. Yeah. So, I mean, I don't know. I should pay attention, but, you know, if you don't want to watch me, it doesn't hurt my feelings. All right, let's talk a little bit about the sample space. Okay, this is very, very useful for figuring out probabilities. The sample space is a list of all possible events. Okay? So, for example, let's say, let me give you an example. I love this example because students apparently love the missed problems because this is too much work. Okay? Let's say that I roll 2 dice, find the probability that I roll a 6 or a 10. Okay? Does anybody know that off the top of their head? Okay? That's what I thought.
1 and 6.
I don't know. We're going to find out. Okay? I don't know what the answer
You
is.
got 2 dice for the 10.
Okay? We'll figure it out. Okay? So one of the best ways to figure this out, and I love dice problems, by the way, and I'll probably put one on the test because some of you don't want to write out the sample space because it takes too long, like you're in a hurry or something. Okay? Is to write out, so let's say I have a red die and a blue die and I can tell the difference. Okay? So I'm going to do a 1, 1, 1, 2, 1, 3, 1, 4, 1, 5, 1, 6. 2, 1, 2, 2, 2, 3, 2, 4, 2, 5, 2, 6, 3, 1, 3, 2, etc. 4, 1, 4, 2, 4, 3, 4, 4, 4, 5, 4, 6, 5, 1, 5, 2, 5, 3, 5, 4, 5, 5, 6, 6, 1, 6, 2, 6, 3, 6, 4, 6, 5, 6, 6. Okay? I know that took a lot of time, but I will tell you, to this day, if I'm doing a dice problem, I'm going to write that out because I want to get it right. Okay? So those are all the options you can get. Now, some people say, well, does the order really matter? And here's how I'm going to answer that. Sometimes yes, sometimes no. Pretend the order always matters and you will get it right. You're more likely to get it right. Okay? So as I'm looking here, a rolling a 6, well, a 5 and a 1 is a 6, right? 4 and a 2, 3 and a 3, 2 and a 4, 1 and a 5. Okay? Rolling a 10. 6 and a 4, 5 and a 5, 4 and a 6. How many circles do I have?
7, 8.
8, right? Just count them. 1, 2, 3, 4, 5, 6, 7, 8. I've got 8 circles. How many total possibilities are there? 36. Okay, that's the answer. I could go 4/18 or 2/9. Okay. So Keaton had guessed 1/6. He would be one of those gamblers that was like, Blaise Pascal, why am I getting this wrong? Okay. Now, by the way, just for fun, 2/9, I think that's 0.2222. Check my math.
You're up.
1/6 is 0.166666, okay? So if you were a gambler and you thought this only happened 16% of the time, and it was happening 22% of the time, would you be happy about that? It would be happening more often than you thought, right? Okay? So so you will find that a lot of the probability problems, gambling is the easiest application. I always love it when I tell people, hey, I teach statistics, and they go, oh, you can help me with my pick six this weekend. And I'm no better than anybody else. It's not like I have any special insights, but I always finish second when I do those. It drives me crazy. I can never finish first. I'm always second.
And what?
Any of those pick 'em games, like, pick all the NFL games, all 14 games or whatever, I'll always end up in second place. Never win. All right. So, yes, sample space can be especially useful. How about, let me do another one, okay? In the book, I don't have a darn eraser. That drives me crazy. In the book, they talk about finite and infinite, which I don't think is especially useful, but I'll just reference it since they do. Okay? Let's do another example. This would be an example of finite, a finite probability. Okay? So let's say that, here we go. I'm going to pick on Zoe has 3 concert tickets. And she wants to take 2 friends. Okay, she's going. It's her tickets. Okay? So her friends are Eddie,
JC.
JC, there you go. What concert are you going to, by the way, Zoe?
Billie Eilish.
Billy who?
Eilish.
Billie Eilish?
Billie Eilish.
I don't know who that is. I thought you were going to say Billy Ocean. I was really like, oh, really that old? All right, and Robert, let's say. Okay. So, what is the probability she goes with the 2 guys? Okay. Let's say she's drawn names out of a hat. Okay. So we're going to put Eddie, JC, and Robert in a hat. Got to pick 2.
Are they all
Okay.
guys?
No, I'm a girl.
JC's a girl.
Well, JC's.
I feel like this has happened before.
Okay.
I knew that.
All right. So one of the easiest ways to do this problem is to figure out the sample space. Before we answer the question, what is the sample space?
All of the list of all the possibilities.
The list of all the possibilities. Who can she go with?
Eddie, JC, Eddie, Robert,
Okay, so we're going to go Eddie, JC, Eddie, Robert,
JC, Robert,
JC, Robert.
and
Now, I always said do this so that pretend the order always matters.
JC.
JC, Eddie,
That's already there.
but I'm saying the order, we're going to, because,
the order matters.
we're going to, if you assume order matters, you won't get it wrong.
Then Robert, Eddie,
Robert, Eddie,
and Robert, JC.
and Robert, JC. Okay? All right, so we've got 6 possibilities, right? She's drawn them out of a hat. Okay? Now, so the probability that she goes with 2 guys, that would be Eddie and Robert. It would be Robert and Eddie. Is that it?
Yeah.
Yeah. So the probability that she goes with 2 guys would be
2/6.
2/6, which equals 1/3. Okay? What is the probability? Find the probability that JC goes.
4, 6.
Okay, I'll pick a different color. Okay, we've got JC, 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 oh, JC, all the green ones, right? So that would be
4, 6.
4, 6, or 2/3, okay? Does that make sense? Okay, our sample space is useful. Okay, now let me give you one more example, because people always get this one wrong because they don't do their sample space. I'm doing good on time. Oh, I was looking for an eraser, but there's not one. All right, so let's say that you flip a coin 3 times and count the number of heads. Find, well, here we go. Let's start here. Here is what we're going to do. Find the sample space. I'm going to do that first. And then I'm going to say to find each of the probabilities. And I'm going to finally ask, are all outcomes equally likely?
That camera getting with it.
Oh, it's not, thank you. That's why you guys are my, okay, there we go. I wonder if it would help to turn out this light too. Is that too dark or is it okay?
It's okay, it's okay.
Okay. All right, so, Ray, what would be the sample space for the number of heads? Flip a coin 3 times. What are all the possibilities?
No, that's a lot, isn't it?
You can do number of heads. Okay? How many heads could you get out of 3 tosses?
3.
You could get 3,
Or 2 or 1.
or 2, or 1. Is that it? Or 0. Don't forget the 0, right? You get 0 heads. Okay? Do you think those are equally likely? I should ask C first. We'll ask that question first. Are 3 heads just as likely to happen as 2 heads, just as likely to happen as 1 head, just as likely to happen as 0 heads?
No.
Should we vote? Who says yes? 1? Who says no? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Who didn't raise your hand? You got it wrong.
Oh. Well,
Okay, so let's find out. Okay, so there's 2 ways to figure this out. So number of heads. Okay, if they were equally likely, some of you think that they're all equal, right? So if they're equally likely, 1/4, 1/4, 1/4, 1/4. We're going to find out if those are the right answers here in a minute. Okay? Yes.
Probably 3 and 0 are equally as like.
Probably. Let's find out. Okay. So we're going to find out. We're going to find out if that's true. Okay. A lot of people will say, "Oh, well, they're equally likely because the head's just as likely as the tail, right?" Don't you all agree that a head is as likely as a tail? So why would it not be equally? Okay. This is a case where order is going to matter. Okay. If I get 3 heads, so another way to write out my sample space would be to write out head, 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 right? That would be 3 heads. Okay. 2 heads, I could get heads, heads, tails. I could get heads, tails, heads. I could get tails, heads, heads, right?
That's tails head.
1 head, I could get heads, tails, tails. I could get heads. No, I could get tails, heads, tails. I could get tails, tails, heads, right? 0 heads would be tails, tails, tails. Okay, so let's look at this. Okay, This is, you could call this a sample space, you could also call this a sample space. This would be the sample space for the number of heads, this would be the actual outcomes, right? So, how many times did I get 3 heads? I got 3 heads, 1, so this is what we would call, I think in the book they call it finite. I would call it theoretical. Okay, theoretical. So I've got 1 out of how many possibilities?
9.
1, 2, 3, 4, 5, 6, 7, 8. Okay, 1 out of 8 heads. How many times do I have 2 heads?
1, 2,
These are all 2 heads here, right? We got 3 out of 8. Okay. How many times do I have 1 head? I also got 3 out of 8. How many times do I have 0 heads? 1 out of 8. Now, if this is a legitimate probability distribution, what should it add up to? It should add up to 8 eighths or 1, right? Okay. So, now that we've seen that, is this column correct? No, they're not equally likely. Okay? Now, a lot of people can say, oh yeah, because a lot of times we think wrong. Our head's just as likely as the tail, so they should all be equally. No, it's not true. Okay? Order matters, and because order matters, and I listed out all the possible orders, now you can see why these are more likely than those. That makes sense? Okay? So that's why I say, once again, if you always assume order matters, you're more likely to get it right. Because if I had just done 3 heads, 2 heads, 1 head, 1 tail, I would have gotten that column. They're all equally likely, right?
how accurate is this? Because if you flip the coin 8 times, you're not going to get every single one of those every time.
That's a great question, because I don't think they picked it up on the camera. I hope this is picking up. He says, how accurate is that? Because if you flipped a coin 8 times, would you get these exact outcomes? No. But you just asked a great question that leads us to what we call the law of large numbers, which I was looking and I didn't see that in the book, but it should be. Okay? The law of large numbers says if you repeat an experiment a large number of times, the actual will approach the theoretical. Okay? Very useful. Now, you know what else I like to call this rule? Or a better definition of this rule? Why the casino always wins and you don't. Because they understand the law of large numbers. In fact, I want to give you another quick example here. Oops, I'm used to turning the monitor. I got to turn this. Okay? So, you go to Las Vegas. Oh, I keep forgetting I don't have an eraser. Okay? You go to Las Vegas and you're betting on a coin flip. Okay? We'll keep this easy. Okay? Heads, you win. Tails, you lose. Okay? Now, let's say that comes up, so you flip it 10 times. Flip 10 times. You're betting $1. Okay? It comes up with 8 tails. How much did you win or lose?
You lost.
Okay? Comes up with 8 tails, you're betting $1 every time. You're gonna lose how much? You're betting $1 every time. You're gonna lose $6, right? You're gonna win twice and you're gonna lose 8 times, so net 6. Okay? All right, so now we're gonna flip 100 times. Okay? Now you're thinking, oh, that was just a fluke, right? It's supposed to be more like 50-50, right? Aren't you thinking that? It's gonna be in your favor. Okay, we're flipping it 100 times. It comes up with 60 tails, is that right? Okay, on the second one, how much are you down?
$10.
You're down $10, right? Okay, so you lost more money, even though it's now 40% heads. It's in your favor, right? The game's getting better. Right, we went from 20% heads to 40% heads. Odds are in your favor, right?
1,000.
We're gonna do it 1,000 times. 1,000 times. It comes up 550 tails, 450 heads. Okay, we've gone from 20% to 40% to 45%, right? How much are you down?
$100.
You're down $100.
How are you calculating that? What you're down?
Just to show you that the casino understand. You think, oh, the odds are going to get in your favor, and they are. You're still losing money. Not only are you losing money, the odds are getting better on your heads, you're losing even more money. You went from 6 to 10 to $100.
At this rate, you're gonna eventually start winning some, right?
That's what the casino wants you to think. Okay? All right, so that's the law of large numbers. That was a really good question, Craig, because this is what could happen. Even though theoretically you should be breaking even after 10, after 100, after 1,000, right? You should be breaking even. You just keep losing money. Okay? The casino understands this.
I'm confused on how you're calculating down, because you did 10 minus, or 8 minus 2 was 6. And that's.
Oh, actually, you know what?
wrong.
We are wrong. This is 60 minus 40, which is 20, right?
So you just
Oh,
subtract the
this- yeah.
bigger one?
Yeah.
Okay.
You lost 60, you gained 40, you're down 20. That one was wrong.
Okay, I get it.
Okay? Okay? Does that make sense? This is why gambling's dumb. There was a big, do you want to make a lot of money? Who wants to make a lot of money? Okay? Become an actuary. Anybody ever heard of an actuary? Actuaries are really good at probability. They had an actuarial convention in Las Vegas, and the people were like, ooh, we're scared. They can probably count cards. We might be in trouble. But the actuaries were like, no, because it's always in the casino's favor. They always, when you see a thing that says 97%, we return 97% on payback on our slot machines, they just told you what their profit margin was. They're making 3%. Okay? They're making 3 cents of every dollar. Yeah, and they'll always advertise, hey, JC from Salt Lake City, Utah won $1 million. You could win too. Yeah, you could win, but you won't. Okay? Because they understand this. All right. So now let's talk a little bit about infinite models. Infinite models. One of the things that they talk about is how many numbers are between, or maybe I should say decimals, how many decimals are between 0 and 1? An infinite number, okay? Now, let me show you an example. Oh, this is a good example. Let's say that you have a friend that is always late. Going to be a he or a she? Any of you have friends like that?
She.
Yeah, my wife has a friend like that. She is always, she is just as likely, just as likely to be 3 to 4 minutes late as 25 to 26 minutes late. What is the probability that she is 5 to 10 minutes late? Okay? Now, this would be an example, and I don't know that this is in the book, but this would be an example of what we would call a uniform distribution. Okay? Uniform distribution says all outcomes are equally likely. Okay? All right, so one of the nice things about the uniform distribution is it's always, and I mean always, I don't use that word very often in statistics, but you can use it here. It's always a rectangle. Okay? So if I were to draw this, this would be 0, this would be 30 minutes late. And my wife's friend is like an hour late. But we'll just say 30 minutes. Okay? So one of the rules that we had was the sum of your probabilities must add to 1, okay? So this area has to be 1, right? Okay? Well, Gentry, what's the area of a rectangle?
Like the equation.
Yeah. Length times width. Okay? Well, if the area has to be 1, right, to be a probability, and the length is what? 30. What does the width have to be?
1/3. 1/30.
1/30. Okay? So that means that is that tall. Okay? So you can always figure out, so whatever your length is with a uniform distribution, just put a 1 over that number. And that will be the width of your distribution. Okay? Now I'm going to erase this for a second. Okay? We want to know the probability that she is 5 to 10 minutes late. We think this is a uniform distribution. Okay? So that would be 5 to 10 minutes late. So we just want the area of this area here. Okay? So in this case, I would also call this a continuous distribution. It's another word you should use, okay? So what is the length, Robert, of that?
The length is the circle area, right?
The circle area.
5.
5, and the height is, or the width?
The width is 1/30th.
1/30th. So the probability that she's 5 to 10 minutes late is
5/30th.
5/30th, which rounds to 1/6. 1 out of 6 times she's going to be 5 to 10 minutes late. Does that make sense? Okay. So what kind of a model did I just demonstrate out of the 3 types of probabilities? Theoretical, because it was based on rules, okay? Now you may want to find out, take 30 events. I don't know, why would you want to do that? No, you're late for 6 of those. Okay? All right. What else do I have? Oh, I'm doing pretty good on time. Okay, so the last thing I want to talk about is independence. I don't think the book talks about independence enough. Okay? Two random, can you see that? Yeah, you can. Two random phenomenon are independent if knowing the outcome of one event does not affect the outcome of another. Okay? So, Dela, if I were to flip a coin and I got a head the first time, I flip it again, is a head more or less likely on the second time?
The same.
It's the same. She didn't go for my answer. Good. I was trying to trick you. Okay? So a lot of times we will refer to independence as memoryless. Okay? The coin has no memory of what happened last time. It's going to act independent. The heads are going to come up the same amount of time. Okay, so why am I having a hard time remembering your name? It's Casey. Casey, if I were to, you play cards?
A little bit.
A little bit. Let's say that I pulled a king out of a deck of cards. Okay? I put it on the table. What's the probability that I draw a second king? So let's do the first king. Probability of the first king is 4 out of 52. Sometimes it's better to leave these unsimplified. Okay, I put that king on the table. What's the probability I draw a second king? 3 out of 51, because that first king is no longer in the deck. Okay? Are these two events, drawing the first king and drawing the second king, are those independent or dependent? Those would be an example of dependent, right? In a way, the cards kind of have a memory, right? They remember that that first king is now missing. Okay? So independence you can think of as a coin flip. Dependence you can think of as cards. And sometimes they're not quite that easy. Let me throw one more at you really quick, and then I'll let you guys go. Let's say that the first event, the probability of an event is earns $100,000 a year. Okay, that's event number one. The second event is probability that the person has a bachelor's degree. Do you think those events are independent or dependent? Does earning $100,000 a year, is that independent of a bachelor's degree?
Dependent.
Or does it dependent? It's dependent, right? That's why you're all here, right? You think that if you get a bachelor's degree, you're more likely to earn $100,000 than if you don't, right? Okay? So this would be another example of dependence. Okay, let me just end with a couple of little stories here. I would do. Let's say I flip a coin 6 times. I get heads, tails, heads, tails, tails, heads. I flip it 6 times again. I get tails, 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 heads, heads, heads. Okay? Who thinks option number 1 is more random than option number 2? Nobody? Okay, one. Who thinks option number 2 is more likely than 1? Nobody? What do the rest of you think? So you think they're equally likely, right? Okay. A lot of times we'll look at these and we'll say, oh, there's a pattern there. That must not be random, but it probably is. It could be random. Okay. In 1986, Evelyn Marie Adams won the New Jersey lottery for the 2nd time. That's not fair. Okay. The New York Times stated the odds of winning twice were 1 in 17 trillion. 2 statistics professors said that the odds of winning twice is tiny, but it is almost certain that someone will win twice. And they said that within the next 7 years, the probability was 1/2 that someone would win twice. Does that seem a little high to you? 2 years later, Robert Humphreys won his second jackpot. Okay? If a family has 4 girls in a row, is the probability of the boy higher on the 5th child? No. Independent. All right, so quiz on Tuesday. We'll be back in our regular class. I think we'll meet there for at least a week or 2. And it'll be on chapter 12, okay? So I will post the homework for chapters 4 and 5 that I didn't post already over this weekend. So make sure you do that too. I will try to post that by Friday.
And fix the test?
Yeah. All right. See y'all later. And hopefully this recorded sound.